Hello Year 11, I just thought I'd take the opportunity in this video to run through half of your revision ready for your Year 11 mock this year. So in this video we're going to be looking at physical landscapes of the UK, focusing on rivers and coasts. So this in the summer will be part of your paper 1, your physical geography. And obviously it must be said that everything I go through today is only linked to that revision checklist that you have been given. It is not everything associated with these two topics that you will need for the final exam in the summer. So to get yourself ready for this video, I'd recommend that you have your checklist available and you have something to take notes on. It would be even better to perhaps have something like flashcards or a big bit of A4 or A3 paper that you can be making a spider diagram on, so that you are creating something that can be referred back to again as you're watching the slides and listening to me go through the key and core areas of study. So if we start on our first section of coasts today, and we have a little bit of a look at the first part of your checklist, which is constructive and destructive waves. So the first thing you need to be able to do here is make sure that you can identify the different characteristics. So if we look at them quite simply at the bottom of this slide, we can see that the constructive waves are much smaller and they will almost spill onto the coastline, whereas those destructive waves are the much higher energy ones. That will be the result of either perhaps a storm or an area where you have got a long fetch, so a long distance over which that wind has blown to build up the wave before it crashes onto the coastline. So in terms of their key characteristics, you need to be able to talk about the swash and the backwash. So swash is upwards movement up the beach and backwash is back down. Constructive waves, as the name suggests, construct a beach. They build up a beach. And the reason for that is that their swash is stronger than their backwash. So there's more upward movement of material than there is removal of it as that water returns to the sea. There's lots of other characteristics as well for your real exam you'll need to make sure you're happy with, such as the height and the frequency of these waves. So constructive waves are much smaller in their height or shorter, and their frequency is much lower. So they hit the coastline less frequently than the destructive, which we will talk about now. So destructive waves are, again, as the name suggests, really destructive on the coastline. They will end up eroding the coastline. And the reason for that is that their backwash is stronger than their swash. So when their swash comes in, it can be quite weak in the kind of movement up the beach, but it will plunge downwards, as you can see in this little diagram here, because the wave is quite tall. So you will get that almost downward gouging out movement, which will create an indent in the beach, as you can see in the diagram. And then that wave will have quite a lot of power to pull material off the beach with that strong backwash. So they're really high energy, they're high wave frequency, so they occur really frequently on the coastline, and they will end up creating quite a steep beach because of that erosion towards the base of it. So another point on your checklist is the idea of understanding the landform of a spit. So here, obviously, we're looking at a depositional landform because, as this photograph is showing you, these things are made of sand that is dropped by the waves to create a finger-like structure or finger-like landform that is poking out almost away from the coastline. So we need to, when we talk about these processes that create landforms, start at the very beginning of the story. You need to make sure that you are thinking about setting the scene and talking about a sequence of events that leads to the creation of these landforms. So if we think about setting the scene, we've obviously got a coastline here that is slightly curved, and we've got longshore drift occurring on this coastline. So it will be that the prevailing wind is coming in at an angle, causing that sediment to move along the beach, and in this case towards where the camera is, so from the back of the photograph towards the front. So that's going to happen periodically, and then what's going to happen is eventually the landscape or the coastline is going to change direction. and that's going to have an impact upon what happens to the sediment. So the longshore drift process isn't naturally going to just readjust itself. It will try and keep going out in the same original direction of the coastline. And as that sediment is pushed into that same direction, it will enter deep water and will get dropped because it will be much lower energy in that region. So you end up getting a build-up of sediment at this section of the coastline. What that means is that when that sediment is built up, that longshore drift can actually carry on along that part of the coastline, along the new sediment ridge, and that will continue to the point at which you're looking at here, where you end up with a long ridge of lots of built-up sediment over time. Now, it's worth noting that the size of the sediment will differ very much across this spit, and that's for two reasons. So you will end up with a smaller sediment at the very end of the spit, so here towards the kind of foreground, the front of the photograph, whereas towards the back of the photograph, at the back of that spit, it will still be much larger. Two reasons for that. The first one is that as this sediment is pushed along the spit, it's going to be subjected to attrition. So the banging together of the rocks as they're moving back and forth in the waves and being moved along the spit will cause them to break away, getting smaller and smoother. But then also there's the idea that actually lighter sediment is actually just going to travel more easily. So it will end up going further along the spit and ending up right at the end. Now, this explains why you end up with a bit of a curve at the end of the spit, because we know this prevailing wind is generally moving in this one direction, pushing the sediment towards the front of the photograph here. But there will be times on this coastline where we get something called a secondary wind. So that's a wind that is in a different direction and will be less powerful than the prevailing wind, or at least less frequent. And when that wind does come in, it will be able to push that sediment inland a little bit. This photograph doesn't have a perfect hook on the end, but if you look at your diagrams in your revision notes and in your revision guides, you'll see that diagrams do show quite a prominent hook at the end of a spit. And that is just because that lighter sediment has been pushed in by the secondary wind. Now, obviously, it's worth remembering behind this spit that you have now got an area that is really sheltered from the wind, and therefore you're going to get lots of deposition because the waves are going to be low energy here, and that will build up eventually to create a salt marsh, which is a second landform, but is also connected to this concept of spit formation. So it's worth noting that at the end of your explanations as you describe how these spits look and explain how they form. So something else you need to be happy with on the coast side ready for this mock is your mass movement processes. So if we have a little bit of a look here, I've tried to find as many Dorset examples as possible. On the top left-hand side, we have got a rock fall. So there are 4 different types we're going to go through, rock fall being the first. You can see that this cliff is really steep and it has got big boulders and rocks at the bottom. So if we look at that in diagram form, this is the sort of thing we should be looking at in the context of a rock fall. So really vertical cliffs. It will be really resistant rock, but not necessarily invincible. It is going to suffer from things like freeze thaw. So if you get lots of temperature changes on your coastline, it could cause weaknesses to get bigger and eventually have these big boulders or rocks break away and fall to the bottom of the cliff. If we look on the right hand side, this was near Durdle Door a few years ago. We've got a landslide. So this is different, and you can already hopefully see why visually. So the sediment is a little bit different, it's finer, obviously not as resistant. You've also got a cliff that is not as steep, that is linked to the type of rock that you're looking at. And then the way in which the sediment moves is much more, as the name suggests, in a sliding motion. So it doesn't fall, it slides down the landscape itself. So it's going to be a much kind of gentler process, although when you actually see them in the flesh, those landslides can still be quite catastrophic. Then on the bottom left-hand side, we've got a mud flow. So obviously this is, again, a different type of rock. This will be something that's quite clay-like, quite muddy if we think about it in a simplistic way. And this is probably going to happen when you've had a lot of rainfall, that the clay becomes really saturated and heavy and can actually end up flowing downhill a little bit like a liquid, sometimes with its own stream within it if it's really saturated. And therefore the view of the end product is going to look very different to what you can see in the two examples above. And the final one I've represented in two photographs here. This is rotational slumping. So this is a slightly different movement. If you imagine, I'm sure that you don't do it on your school chairs as you're in your lessons, but if you imagine that kind of slumping that you will see some students doing and what their back is doing, it's quite a kind of curved movement, isn't it? Their back is curved, they're kind of sliding or slumping downwards. And that can happen when you've got quite sandy geology, so your rock type is quite sandy, and you'll end up with these almost detached different levels on the cliff. So if I show you that in a diagram form, you're going to be looking at something that looks a little bit like that. So note how curved that movement is, and also how you end up with those different levels of the cliff top itself. So something else with your coasts section for your mock that you need to be happy with is hard engineering. Obviously, we also know soft engineering, but we're trying to keep things a little bit more structured and almost a taster of what you'll have in the real thing. So please don't forget there is obviously soft engineering as well. But for your mock, you need to make sure that you're happy with seawalls, groins and rock armour, and that you know how to describe them. So literally as if somebody hadn't seen them before, what is it? And then also explain how it works. So make sure that you can explain how it impacts upon the coastal processes. So if we take the seawall for an example, if we had to describe what it was, then we talk probably about the fact it was made of concrete. We talk about where it's built, so parallel to the coastline. And then we also talk about how it works. So you need to talk about the fact that it is going to be reducing erosion. It's allowing the waves to break on it rather than on the cliff or the town behind it. And then some of them as well can also be curved, can't they? So as well as those waves breaking on it, they can also refract that energy on a curved seawall, which is why a lot of them are now more curved in shape. That is better. We don't need to evaluate in your mock, but it's worth noting that curved seawalls are actually better because they send the energy back into the sea rather than having to absorb it in the concrete itself, which means that you're not going to end up with as many cracks. So make sure that you can do that for groins and rock armour. The key thing to obviously note with each of these two things is that groins, their main focus is stopping longshore drift, and you need to be able to explain how they do that and why that's important. And then also with the rock armour, the key difference between seawalls and rock armour is that rock armour dissipates the energy of the wave. So when the waves hit them, then it's going to dissipate into each of the cracks and holes between the rocks and break that energy up so that when it does hit behind, if it does get that far, it's not going to be as energetic and destructive. You'll notice in that number 3 image that actually there is a seawall behind it. So sometimes rock armour is used to break up the energy before it hits the seawall to prevent that seawall from having to take the brunt of the force of the wave. And the final thing for coast is that you need to be happy with erosional landforms. And in the context of this mock, caves, arches, stacks and stumps, it's worth noting here that it's probably worth you checking you're happy with how headlands and bays are also formed, because that will be the start of the process we're just about to talk about now. So talking about the idea that a headland is obviously a mostly resistant piece of rock that is sticking out into the ocean and how that has come to be. So if we think about the fact that this headland is really exposed, it will be resistant, but it will be exposed to powerful waves, so it will be subject to a lot of hydraulic action from those big waves out at sea, and also obviously it will also have its faults within it, and that hydraulic action will find those faults and make them bigger. So eventually those faults will all join together through those processes of hydraulic action and corrosion to the point where they create a cave. And that will actually continue to get bigger and bigger as those waves continue to attack the headland. It's worth noting, obviously, that there's some sediment gone missing there. It will be in the bottom of the cave and actually be used for abrasion and almost like as what we call an erosive tool. So the waves will be able to use those rocks that have collapsed into the sea to fling against the side of the headland and increase the rate of erosion to the point where this cave is going to go all the way through the headland, and then you end up with this arch. So that erosion will continue, but it's worth noting here that another important factor that will have been happening all the way to this point already, but becomes quite a main kind of process, is the process of weathering. So you're going to get a lot of weaknesses being created on the top of the headland, so biological weathering, chemical weathering, and that will weaken the top of the arch, whilst as well it is getting wider at the base through the force of the waves. So eventually that will then collapse to create a stack, which will be separate to the rest of the headland because that arch top has collapsed in. So you need to talk about that collapse and the idea that obviously gravity will have played a big part there as well, and also that collapsed material will be used for abrasion within the water itself. And then something that this diagram fails to show is the last part of the process. So obviously that stack is out at sea, it's on its own, it's very tall. As it's eroded at the bottom, it will become really top heavy, so it will collapse to create a stump. So if we look at Old Harry Rocks as the most famous example in the UK of this sort of landform, but also a local one, so some of you might have your own experience of this area as well, you'll notice that if you look in the far right hand side, there is a little bit of a kind of white area in the sea where the waves are breaking over a shallow piece of land, and that's the stump. So that will be sometimes exposed at very low tides, but generally is going to sit under the water. So you need to make sure that you're okay with identifying each of those different parts of this process within a landform, because they're not always going to be in that perfect sequence. So here you can see that the arch is before the cave. There's a gap where an arch has collapsed. There's a wave attack zone that you can see by the different colour on the chalk because of all the algae growing on it. Because it's frequently wet and hit by those waves. But you just need to make sure that you are able to identify the different elements of that process, because it's not always going to look like the perfect sequence you saw in that diagram. Okay, so let's get on to rivers now. So this is going to be the second half of this part of your mock. And the first thing you need to make sure you're happy with is, first of all, what a long and cross profile of a river is. So if we think about a long profile, that's the bottom image that you can see here. And that is effectively a diagram to show the journey from source to mouth of a river. The cross profile or a cross section is the brown and blue diagrams that you can see at the top of this slide. So imagining that you've sliced this river right down the middle like you would a Colin the Caterpillar cake, and you're looking through the kind of the center, I suppose, of that cake. So here you're obviously looking at what the river looks like through almost like down the inside of it, really. So the upper course is going to be very different in its shape, in its cross profile. It's going to be really narrow because it's going to be running through quite hard, resistant rock and often V-shaped valleys. But it is going to be deeper than it is wide because there's going to be lots of vertical erosion happening here. So it's not going to be very deep, but in relation to its width, it's going to be deeper because you're going to get lots of vertical erosion, which is gravity pulling on the water downwards and creating more of a downwards erosive force. As we go into the middle course, then you are going to have it starting to become wider, and that's because the water has more space now. It's able to swing around corners, as we know as meanders. It can sway all over that floodplain and begin to erode on the sides of the riverbanks, as well as becoming wider. That's still going to be happening. So more of that lateral side-to-side erosion, creating a wider cross profile. And that will continue into the lower course, where you have got the deepest and widest river, because all of those vertical and lateral erosion processes have continued. There's more water because you've got water joining from lots of tributaries to join into the main river. So this is going to be the widest and deepest cross profile. In terms of landforms for your mock, you need to make sure that you can recall the process of a meander and how it forms, and also in particular its different features along its own cross profile. So the almost rule to remember here when we look at meanders is the fact that water will be flowing faster around the outside bend of a meander, and that's where you're going to be getting the erosion. And then on the inside bend, it's going to be moving more slowly, so you're going to end up with more deposition because the water doesn't have as much energy. If we look at that as a cross profile, so slicing it here from point A to B, you're going to end up with something like this. So you can see where you've got that deposition in the closer to the A mark, and that's going to be the kind of feature of a slip-off slope. Looks a little bit like a beach, doesn't it? But that's where you're going to get sand and shingle dropped off on that inside bend. And then on the outside bend, obviously you've got high levels of erosion, so you've got undercutting of that riverbank creating a river cliff, and obviously it does have lots of information here as well about the idea that because, for example, it's faster on the outside bend, that's when you're going to get more sediment held in that section. In terms of your river processes for your mock, make sure you're happy with the processes of transport. So here we have got 4 different ways in which sediment can be transported, and it all depends on the size of the sediment. So if we start with smallest to largest, then we have got, first of all, the top left-hand side, we've got somebody being suspended in air there. So I'm trying to kind of give you visual ways of remembering these key terms today. So suspension is the first way in which water is transporting sediment. So if it's super, super fine, then it will be moved within the river itself. Smaller sediment as well, particularly quite soluble materials, will be dissolved within the water as well. So we have got solution occurring if you've got minerals that are able to be dissolved in the water and moved downstream in that process. And then we look at the heavier material. So we're actually going to need to look at the heaviest first here because that's the order of my animation. So the heaviest material is probably not going to really lift off the riverbed. And you need to think of this almost as traction on a tyre, which is where the word traction comes from, traction meaning grip. So these large boulders will be rolled along the riverbed, and probably not very often, only when there's really high flow, perhaps after a storm. There will be smaller rocks on the riverbed as well, and they will be moved through the process of saltation, so the bouncing movement that will occur as the water is moving past those bits of sediment. In terms of your management for rivers in your mock, this time it's soft engineering, so making sure that you know how rivers can be managed without the big man-made structures such as embankments and things like that. So the 4 ways in which we've looked at this in school were floodplain zoning, so where you put your less important, so maybe less important economically or in terms of socially, stuff at the bottom. So that's going to be maybe farming, areas are going to be closer to the river, playing fields, car parks, anything that doesn't have a high economic or social value. And then the more important things are going to be put away from the river itself. So potentially these areas will be free from flooding if it should happen because they're higher up. So if you think about Dorchester, right at the top of Dorchester, we have got the Thomas Hardy School, obviously very important, and we've also got the hospital and quite a lot of industry. So these areas have been specifically put away from the river at the bottom near the youth club, where you'll know that there are things like a play park down near the river, because if that river does flood, then theoretically that won't be quite as traumatic as if the school flooded. In terms of soft engineering as well, it's literally sometimes just a case of making sure everybody has information. So predicting that heavy rainfall is going to come in, so the Met Office will be in charge of that. And then the Environment Agency are in charge of making sure that that knowledge is appropriately spread across both the general public and also any other stakeholders, so industries or governments or councils that need to make appropriate decisions with that information. And that means that locals and councils can make plans ready for a flood, such as putting sandbags in places. You can get these special flood gates and barriers that you can put on door frames so that water isn't going to go into homes. It allows people time to make preparation. Then we also looked at afforestation, which is the concept of planting trees or planting other vegetation to make sure that when the water does come up, that actually the roots are holding the soil really well. So you're not going to get collapse of riverbanks. You're not going to get soil erosion that's going to, unfortunately, in some cases, what that would do is it would actually remove all the nutrients from the soil. But it also actually stops there being as much water in the river in the first place, because obviously trees will intercept and soak up water and therefore reduce the risk of flooding in the first place. And the final thing is river restoration. So in coasts, we have something similar, which is managed retreat, where you just identify parts of your drainage basin that actually could almost act as a bit of a sponge to any high levels of water that might come in. And that will reduce stress on other parts of the drainage basin that need to be protected, such as towns and cities. Looking at your last landform for coasts, for rivers, is that you need to make sure that you are okay with waterfalls and gorges. They are two landforms that are formed through the same sequence. So a waterfall retreating upstream will create a gorge. So let's look at this again in the form of a sequence of diagrams. So if we think about setting the scene, we're going to have a river flowing downhill over hard and soft rock. And some important things to note here in terms of key terms is that this is likely to be in the upper course of a river, and you're likely to also have lots of vertical erosion as a result of that. So that's that downward erosion that's going to end up with this happening. So the softer rock being eroded more quickly than the harder rock to create a rock step. Now, as that continues, you're going to end up with the water causing undercutting of the harder rock and the creation of a plunge pool, because as that water falls down, you are getting lots of that vertical erosion through that process of hydraulic action, the shear force of the water falling down off that overhang and falling into the plunge pool. Now, that overhang is hard rock, but as we've said multiple times already in this video, hard rock is not invincible, so it will have weaknesses in it and eventually it will crack, and that will occur due to gravity, and ultimately then all fall into the plunge pool and actually increase the amount of abrasion occurring, because you've got those rocks swirling around in that plunge pool acting as an erosive tool. Now, eventually that will continue to the point where that hard rock will continue to collapse and retreat here to the left of the diagram, but in real life it will actually be going upstream, and that will create the second landform of a gorge. So if we have a little bit of a look at this image here, you can see how, or imagine how, this waterfall was actually closer to the point at which the photograph was taken, and over time it has retreated backwards as the hard rock has collapsed into that plunge pool. So in terms of content, that's where we're going to end, because as we said, the mock is just a taster of this topic, but just some key tips really in terms of this particular part of your exam. So physical landscapes, rivers and coasts, these questions don't ever exceed 6 marks. So you therefore need to have more of a focus on the accuracy of your description and explanation of landforms. So making sure that you're using your key terms really well, putting them in. So try not to use the word erosion. Try and think about what type of erosion, for example, is happening. Making sure that you're explaining formation of landforms in a clear and detailed sequence. So as we've done today, set the scene and talk about a step-by-step process that leads to the end result of that landform. There is some understanding needed of how human intervention on the coast and in rivers will actually have an impact upon the river and the coast. So making sure that you can talk about how processes, for example, on the coast are halted or prevented by putting something like a seawall up. And the last thing is that within all of your geography exams, but in particular this one and your mock, you need to make sure that you have got some basic mathematical skills ready. So you're going to need a calculator, and you're going to need to be able to work out simple calculations like mean, median, mode, and percentage, as you may be given some geographical data with which you need to be doing some of those calculations. So I'll stop there and just wish you all, on behalf of the department, lots of luck in the completion of this mock. We hope that you're able to show all of the hard work that you've put in over what's been quite a challenging GCSE year and a bit. And just to remind you that you have lots of resources available to you. You've got your notes from your lessons. Most of you should now have a revision guide. And you've also got lots of recommended activities from your teacher that have come through either in preparation for mocks or even just as you were preparing for your physical landscapes end of unit test in year 10. So yes, best of luck everybody. And yes, thank you for listening.